All right, welcome to this explainer. If you're prepping for your radiography exams and feeling a little overwhelmed by the sheer volume of CT physics, you are in exactly the right place. Today, we're going to strip away all the intimidating complexity of this topic. We're going to track the fascinating step-by-step journey of an X-ray. We'll follow it from the exact moment it leaves the scanner's tube, pushes through the patient, hits the detector, and ultimately transforms into a diagnostic image on your screen. Get ready, because we're turning these concepts into absolute high-yield exam gold.
Okay, let's dive right in. Here's your ultimate study plan for today. We're going to cover the basics of attenuation, then move into reconstruction, pixels and voxels, Hounsfield units and windowing, radiation dose and safety, and finally, a high-yield rapid review. Let's get to it.
Starting off with Section 1, Basics, Attenuation, and Physics. So before a CT scanner can actually create those beautiful cross-sectional images you're used to seeing, it has to measure a weakened beam, right? When an X-ray passes through a patient's body and naturally loses energy, we call this weakening attenuation. It's like dense stuff, like bone, well, that stops a ton of X-rays. Less dense things, like the air in the lungs, barely stop any at all. To actually calculate this, the scanner uses something called the linear attenuation coefficient, or just mu for short. And mu depends on three specific things: the tissue's atomic number, its physical density, and the X-ray energy itself, the kVp, which dictates the beam's penetrating power.
Now hold on, don't panic here. I know this equation, the Beer-Lambert law, it looks like an absolute trap for your exams. But let's just slow down for a second, because really, it's just a super simple story of before and after. It's literally just math describing how a beam gets weaker as it pushes through tissue.
So let's systematically break these variables down step by step. In is exactly what it sounds like, the radiation going in, leaving the X-ray tube. I out is what actually makes it through the patient and hits the detector. Mu, like we said, is the tissue's attenuation, and X is just the thickness of that tissue. Because the scanner's computer already knows exactly how much radiation went in, and the detectors measure exactly how much came out, the math is easy. It just solves for mu, the tissue in between. That single calculation, that is the literal foundation of every CT image.
Moving right along to Section 2, Reconstruction. This is all about turning that raw data into actual images.
Okay, so the scanner spins around the patient, grabbing raw data from thousands of angles. But raw numbers aren't going to help a radiologist, right? To build the actual picture, modern scanners use a process called Iterative Reconstruction, or IR. Think of IR like a really obsessive computer just constantly checking and correcting its own homework. First, it makes a rough guess at the image. Then it predicts what the raw data should look like if that guess was right. It compares that prediction to the actual real-world data it just collected, finds its errors, corrects them, and just repeats this loop over and over and over until the image is near perfect. Now listen up, because this is a massive, high-yield exam point. You absolutely have to know the difference between the older method, filtered back projection, or FBP, and the modern method, iterative reconstruction. FBP is super fast, it uses barely any computer power. But the downside, it gives you way more image noise and those really annoying star artifacts. IR, on the other hand, gives you beautifully clear images with less noise and far fewer artifacts. The catch is that IR needs serious computing muscle. It's slower, and honestly, if you push the algorithm too far, it can make the tissue look weirdly smooth or kind of plastic. Now, what is really interesting about this is the number on your screen. Because iterative reconstruction is just so incredibly good at cleaning up image noise mathematically, it means we can drastically lower the amount of radiation we shoot into the patient. Switching to IR can actually give you a dose reduction of around 40%. Seriously, highlight that 40% number in your exam notes right now.
All right, on to Section 3, Pixels, Voxels, and Resolution.
So the image is reconstructed. Let's talk about how it actually shows up on the monitor. I want to test your active recall here for a second, because this is a classic, absolute must-know exam question. What is the fundamental difference between a pixel and a voxel? Got your answer locked in? Let's see if you nailed it.
Okay, so a pixel is just a tiny, flat, two-dimensional square on your screen. Most CT images use a grid, a matrix of 512 by 512 of these little pixels. But humans aren't 2D, right? So when you add depth to that flat pixel, specifically the slice thickness of the CT scan, it turns into a 3D block of tissue. And that 3D block is your voxel. Simply put, voxel equals pixel plus slice thickness.
And you know, how we actually shape those voxels matters a ton for image quality. Here's a great memory trick for your exam. ISO means equal, right? So isotropic resolution means the voxel has equal dimensions in every direction. It's a perfect little cube.
maybe 0.5 by 0.5 by 0.5 millimeters. This gives us perfectly sharp, beautiful 3D reconstructions. And isotropic, though, that means unequal. The z-axis is thicker, turning it into a long rectangle. And that uneven shape is exactly what causes those jagged, ugly stair-step artifacts when you try to look at the scan from different angles. Just remember, ISO equals equal.
Section 4 already. Let's get into Hounsfield units and windowing.
With our 3D voxels built, the computer has to assign numbers to represent how dense the tissue is in each block. I want you to take a mental photograph of this table. These are Hounsfield units, or HU. The scale is anchored by a few super easy memory points. Think of water as the baseline. It is exactly 0. Air, which blocks practically nothing, is -1000, and it shows up completely black on the screen. Bone, on the other extreme, blocks a ton of X-rays, so it's +1000, and shows up bright white. Fat just sits a little below water, usually between -100 and -50.
Here's the thing, though. A CT scanner records thousands of these Hounsfield units, but our human eyes, we can only distinguish about 60 to 80 shades of gray. That's exactly why we use windowing. Window width controls the contrast, while the window level controls the overall brightness, usually centered right on the specific tissue you're trying to look at. And here's a crucial rule you cannot forget. Any tissue with a Hounsfield value above your chosen window range is just going to look plain white. Anything below it gets completely clipped to solid black. So if you're looking at lungs, you need a wide window like 1500 to see all those drastic differences. But if you're looking for a tiny, subtle bleed in the brain, you need a really narrow window, like 80, to catch that subtle contrast.
All right, moving to Section 5, radiation dose and safety.
We absolutely cannot talk about CT without talking about the biological cost. CT delivers a significantly higher dose of radiation than your standard plain film X-rays. And you are 100% going to be tested on the difference between these two metrics. First, CTDIvol. That's the volume CT dose index. This is the average radiation dose delivered in just one single slice. We measure it in milligrays using these standardized acrylic phantoms, 16 centimeters for heads, 32 centimeters for bodies. But here's the catch. A patient doesn't just get one single slice, right? That is where DLP, or dose length product, comes in. DLP measures the total radiation burden for the entire scan. You find it by simply multiplying the CTDIvol by the total scan length. So naturally, a longer scan length means a higher DLP.
And because of that radiation burden, absolutely everything we do in CT is governed by ALARP, as low as reasonably practical. Now, the goal here isn't zero radiation. Zero radiation means no image. The goal is the absolute minimum dose needed to safely answer the doctor's clinical question. We do this using tools like automated MA modulation, which actively dials the X-ray tube current up or down depending on how thick the patient's body is. We also use DRLs, or diagnostic reference levels, to make sure departments aren't creeping up their doses over time. Just remember for the exam, DRLs are national benchmarks for departments to compare themselves against. They are absolutely not strict legal speed limits for an individual patient.
And finally, Section 6, the high-yield rapid review.
All right, we've tracked the whole journey of the X-ray, from the tube, through the math, into the computer, onto the monitor, and factored in patient safety. It is time for the final sprint to just lock this into your brain. Here are the absolute crucial points you need to recall instantly. Ready? Filtered back projection is fast, but noisy. Iterative reconstruction is slower, but gives a massive 40% dose reduction. Next, Hounsfield units. Air is -1000, water is 0, bone is +1000. Windowing. Width equals contrast, level equals brightness. Dose. CTDIvol is the dose per single slice, while DLP is the total scan burden. And finally, voxels. Isotropic means equal dimensions, which prevents those nasty stair-step artifacts so you get perfect 3D images.
Which leaves us with a pretty fascinating challenge as we look to the future. With iterative reconstruction already slashing radiation doses by 40%, as our CT algorithms become even more advanced, how incredibly low can we push that radiation dose before we actually start losing the vital, life-saving details hidden inside those pixels? It's a delicate balance of physics and patient safety, and it's something you'll be managing every single day of your career. Keep studying, keep reviewing these high-yield concepts, and you are absolutely going to crush your exams. Thanks for hanging out with me on this explainer.